Okay, good morning, everyone, or good afternoon. I guess it's already noon. Okay, so are there any questions or concerns regarding anything we've discussed so far? Right, so in the last lecture, we formalized the notions of a dictionary, and we actually talked about certain algebraic concepts like a basis and when is a basis feasible and what is a basic feasible solution, right? And you will be proving on one of your on your assignment too uh, that basic feasible solutions are exactly the extreme points of the corresponding polyhedron. Okay, so it's not too difficult to prove using a previous theorem that we already proved in the lectures. But anyways, let's continue with our algebraic treatment of stuff, right? So I want to write down one of the dictionaries, and I want to talk about canonical forms, which are basically equivalent to dictionaries. So let's just recall the second dictionary from our first example of the simplex method. For EZLP, that's what we called it. Okay, so the basis was columns 1, 5, and 7, and the value was 20. You might recall we found an optimal value of 21. So this was basically the dictionary before that one. And here is what our dictionary looked like. The objective function is here. And the basic variables x1, x5, and x7 are all written in terms of the non-basic variables, just like the objective function, right? Okay. So this is what we are calling a dictionary, right? And we also formally defined a dictionary in the last lecture. So the text that we are following by Ginnen, Kahneman, and Tunchel, they don't actually use dictionaries. However, dictionaries are used in various other texts because they are much simpler to understand and also execute simplex when you're, especially when you're seeing it for the first time. There is another way to do it, which is called canonical forms. And I want to talk about that as well, because it has some advantages, especially when you're trying to do the more theoretical aspects. So this dictionary in canonical form is as follows. We are going to write it basically in SEF LP, right? But there are certain special properties, which are also the properties that we are using in a dictionary. So what is our objective function? It's notice that this is exactly 20 plus x2 minus x3 minus x4 minus x6, right? I'm just writing everything in vector matrix notation. And what do we have here? Well, we want to write down these three equations, and we want to have on the right hand side the constants that we see, 4, 1, and 2, right? Um, and what do we have on the left hand side? We have the coefficients. So we are going to bring everything from the right hand side to the left except for the constant, right? So we get, let's first put down the basis columns, right? We know they have to be identity. So this is, let's just put here 1, 2, 3, 4, 5, 6, 7. So we are going to have a 1 here and a 1 here. And these are our basis columns. And now let's plug in the rest. So I'm just going to copy it down from my notes. So we have 0, 1, 1 here, 1 minus 1, 0, 1 minus 1, 1, and 1 minus 4 and minus 2. Okay, and of course x. Okay. So we are going to call this NLP in canonical form for the basis 157. Okay, and let's just write down what the properties are. So let's write down a formal definition. Consider the following SEF LP. Maximize C transpose X plus S subject to AX equal to B and X at least 0. We are going to say that this LP is in canonical form for the basis V if it satisfies certain properties that we have been using throughout in our discussion in the last 2 lectures. So let's call this LP as LP. Why not? We say that this is in canonical form for the basis V if the following hold. Right, so the first property we want is we want the submatrix formed by the basis columns to be an identity matrix. And notice that we also want the objective function in the dictionary to be written in terms of the non-basic variables, which basically means that the basis entries are all going to be 0 in the objective function. Right? So the second property we want is we want CB to be equal to 0, where CB denotes those entries of the objective function which are corresponding to the basic variables 1, 5, and 7 in this example. Okay.
Sir, could you just repeat what CB was? I could not get it.
Right. So C is our, in this example, C, this is C transpose, right? And what I'm saying is I want the basis entries 1, 5, and 7 to be equal to 0. So CB is the same notation, just like in the matrix. When we say capital B, we are referring to the basis entries. In the same sense, for the objective function, we have 7 entries. 3 of them are corresponding to the basic variables, and 4 of them are corresponding to the non-basic variables. Does that make sense?
Yes, sir, I got it.
Yeah. Okay. So it's the same notation. Okay. And if you have, so notice that here I'm not saying that the basis is feasible. So the right hand side could be negative. We are allowing that in the definition, right? It won't be a feasible basis if the right hand side has any negative entries. Okay. So the corresponding basic solution if you have a canonical form, which is basically the same as dictionary, as you can see here, the corresponding basic solution is just going to be set the basic variables to the right hand side and the non-basic variables to 0. So I'm going to set the basic ones to the right hand side and the non-basic variables to the 0 vector. Right, so in our example, we get x bar b to be 412 and we get x bar n to be all zeros. And this is a basic feasible solution if and only if the right hand side is non-negative, right? So we are allowing in the definition the right hand side to be anything, and it will be a feasible basis if and only if the right hand side is going to be non-negative. Okay, so the main point I want to make is that canonical forms are equivalent to dictionaries, but each of them has its own advantages. So the advantage of dictionaries, I think, it's much easier to understand than to actually run simplex yourself. In fact, even computer implementations of the simplex method actually use something similar to dictionaries, right? Because it's very simple substitution. So computationally, it's not very expensive. Right? So it's easier to perform simplex. However, canonical forms, because you have a matrix and vector and everything, it's just more convenient if you are doing some more theoretical stuff. So if you're trying to prove things about the simplex method, you might find this format easier to work with. So I like to talk a bit about both of them. So let's suppose you are given an arbitrary LP and someone tells you that this LP has a feasible basis, right? So it doesn't have this nice form, identity matrix and the objective function having zero in the basis entries. You don't have that form. You're given an arbitrary LP, but someone tells you that, hey, here is a basis, which may or may not be feasible actually. Can you convert your arbitrary LP into canonical form or dictionary with respect to that basis? And how would you go about doing that? That's what I want to discuss today, right? Because you may not actually have an LP in a nice form. Okay, and the next thing we'll talk about is how do you actually find a feasible basis if one exists. But for today, let's just say we are given a basis which may or may not be feasible. How do you convert your given LP into canonical form for that basis? Okay. All right. So we are given an LP which is an SEF. We already know how to convert any arbitrary LP into an LP in SEF so that they are equivalent, right? So that's not a problem. How do you convert an SEF LP into a canonical form, which is the same as dictionary, for a given basis? Right? So, let's see. I want to do an example on the side and also show you the theoretical translation of it. So let's say we are given an SEF LP, maximize C transpose X plus some constant. Let's call this LP. And let's say we are given a basis of the matrix A, right? So it's a set of m linearly independent columns. So our goal is to write an equivalent SEF LP in canonical form for the given basis P. Okay, so that would be something like maximize. Instead of C, we might have a different objective function which will be equivalent to the original one, subject to A tilde x equal to B tilde and x at least 0. So we need to figure out what all these are. Okay, and these should satisfy the canonical form conditions that we discussed. In particular, we want A tilde B to be an identity matrix and C tilde B to be 0. Right? So we need these two properties. Okay, so let's first deal with the easy property. This one is quite easy. Can someone tell me how would you go about making sure that the basis columns have the identity matrix? Let's
We
do an
can do
example.
row
Yeah,
operations. We can do some row operations or something.
we can do row operations. Can you give me a more direct way of doing it? So row operations is what we were doing in dictionaries. Now I want to view it in a more direct way. If you want to get the identity matrix, can you do something more direct to get the identity matrix in that position? Let's also do an example on the side. I'll give you a hint. Can you multiply by something? Right, so in this example, if I'm given the basis 1, 3, so these are the two columns I'm looking at. Clearly, this is a basis. You can check that this matrix AB 4, 5, 6, 8. You can see that this is invertible because neither of the rows is a multiple of the other row, right? It's just two rows, so it's easy to check. So can we use this matrix and do some operation here so that we will get the identity matrix in those two columns, column 1 and column 3.
We can multiply by the inverse.
Exactly, that's what I was looking for, right? So we can directly multiply by the inverse of this and we will get the identity in those two columns. Right? So let's compute the inverse of this, and I already did it. So just to remind you, for 2 by 2 it's very simple. I never remember these formulas, so I don't expect you to remember them either. Right, so you swap these two and you negate these two. Okay, and if you do that here, you would get exactly the following. 4 minus 3 minus 5 over 2 and 2. Okay. So if we multiply both sides of the ax equal to b on the left by the inverse that we have written down, we will get the identity matrix in those two columns, right? All right, so let's write that down. So this part is actually quite simple. If you want to get a tilde and b tilde, you are basically multiplying both sides on the left by ab inverse. So this part is fairly clear. Okay. Good. All right, so that's fairly straightforward. I suppose everyone can do it and write it down for this example, right? I think I have it written down, so maybe I'll just copy it down. So if you do that, in this example, you would get 1, 0, minus 17, 14, and 0, 1, x equal to 19 and minus 14. So this is our a tilde and this is our b tilde. Okay. Notice that in this particular example, the right hand side b tilde is actually not non-negative. So at this point, you can already conclude that the basis given to us is not a feasible basis. Right? That's not a problem. The procedure we are discussing applies to any basis. Right? So in general, we'll be applying it to feasible basis because that's what we really care about. So now we still need to work the second part out. So how do we make sure that the objective function has this property, that the basis entries are all equal to 0? This is property 2, right? Okay. All right. So, well, if you think about what we are doing in this dictionaries, right? At every point, we are just doing row operations, right? So we are going to do the same thing. We want to do some kind of row operations and make sure that the objective function, those entries become 0. So we want to basically take some linear combinations of the given constraints, add them to the objective function, and get this property that we are looking for. So in particular, here is the plan. Let's multiply the first constraint. So the constraints we had in the original LP were this, right? Right, this was our ax equal to b. So let's multiply the first one by a y1 and the second one by y2 and see what happens, right? So let's say so y, we need to figure out what these y1 and y2 are so that our objective is met. Right? So that basically means that I'm multiplying on the left by this vector, the y vector. And that means that I can also just rearrange things and get 0. Right? So y1, y2 times 6, 2 minus y1, y2 times whatever the left hand side is. This is true for any feasible solution and for any vector y, right? We are just doing some simple manipulations. So this holds for all feasible solutions and all vectors y. And we are going to add this to our objective function because this is 0, right? So we can add this to our original objective function and then force the y1 and y2 in such a way, or choose y1 and y2 in such a way so that the entries in the objective function corresponding to the basic variables will become 0. So we need to figure out what the formula for y is that will force that. Okay, so our original objective function is C transpose x plus S. And let's remind ourselves what it was. It was 2 minus 6, 4, x plus 13. And I can always add 0 to this. Right? So I can always add this whole thing over here. Okay. I think I forgot to put an x here. Notice that certain things here evaluate to a constant. 13 is a constant. y1, y2 times 6, 2 will be a constant because we will pick a specific y1, y2 and plug it in here. And the rest of the stuff is actually in terms of x. So the rest of the stuff looks like this. 2 minus 6, 4 minus 4, 2, 5, 6, 10, 8. Sorry, I forgot to put y1, y2. This is going to be our S plus Y transpose B. Notice that 6, 2 is basically our right hand side here. And what do we have here? This part here is our original objective function, 2 minus 6, 4. So this is C transpose minus Y transpose A. Okay, that's all we have done. Okay, our original function was C transpose X plus S, and all we have done is we've added a 0 to it. What is our 0? It's Y transpose B minus Y transpose A times X, which we know is always 0 because X is a feasible solution. It's some feasible solution, right? All right, and what we want to do is we want to make sure that if you look at these entries in this objective function, if you look at the basic entries, you will get exactly the 0 vector over. So property 2 is the same as saying that I want C transpose B minus Y transpose AB to be equal to 0. I just want the basic entries to be exactly equal to 0. Right? And I can always do this because now I can just compute my Y based on this equation. Right? So what does this say? This is the same as saying that Y transpose AB is equal to C transpose B, right? And which is the same as saying that Y transpose is C transpose B times AB inverse. So if I choose Y transpose to be this thing here, I will get zeros in all the basic entries in my objective function. Do you all agree? Choosing Y transpose as per this formula ensures that in my new objective function, which is going to be C tilde, this is a transpose of it. Right? So that's exactly what we are going to do. We are going to choose Y as per this formula. And if you do that, you make sure that the new objective function, which is equivalent to the original objective function, because we just took the original and added a 0 to it based on our constraints, right? And this will ensure that all of those entries become 0 because we just chose Y as per this formula. And that's exactly what we are going to do. So this tells us how to convert any LP into a canonical form if you are given some basis. Right? The constraints are very simple. You just multiply by the inverse of the matrix. However, for the objective function, we are doing something slightly more fancy. Right? And this is our new constant S tilde. Are there any questions or concerns at this point? So I'm not doing it for the example. I suppose you all can do it. We already have the inverse of the matrix, and you just need to multiply it by this vector CB transpose, and then you plug it into the formula that we have. I'm going to put this all down as a proposition. So this is proposition 2.4. So given any LP, let's say it's called LP in SEF, right? So these are our constraints, and the basis B the following LP is equivalent to the given LP, and it is in canonical form for the given LP. For the given basis, sorry, for the basis B. Okay, and let's see what it is. So we are maximizing. This is our new C tilde, C transpose minus Y transpose A. Times X plus our new constant is the original constant plus Y transpose B. This is our S tilde. This is our C tilde, or rather C tilde transpose. Subject to, the constraints were much simpler. We are just multiplying by the inverse. Right, so this here is our A tilde, and this here is our B tilde. And we still have the same non-negativity constraint, where most importantly, the vector y is computed as per the formula. So y transpose, I mean, I can also take the transpose on both sides and make it simpler. So y is AB inverse transpose times CB. Just for the sake of notation, this is the same as first taking the inverse and then taking the transpose, which is the same as first taking the transpose and then taking the inverse. Okay. So if you follow this, you're given a basis, you can convert any LP into canonical form for that basis. And if you have canonical form, you can also write down the dictionary, right? It's simply a rearrangement. But you can see why canonical form is a bit easier to talk about, because you can actually use a lot of linear algebra stuff to make things more formal. Right? So using this proposition, you can convert any linear program into canonical form for a given basis. Are there any questions or concerns regarding how we got to this proposition? I mean, we essentially proved it, right? We essentially found out what we need to choose y so that we make sure that those entries become 0 in the new objective function. Right, so maybe I'll give it as a do it yourself. Compute y for the given example and write down the LP in canonical form for the basis b equal to 1 and 3. Are there any questions or concerns regarding anything we've discussed so far? This whole idea about multiplying Can you all hear me?
Yes, sir. Now you're audible.
Yeah, sorry, there is a power cut here, so I had to switch to my hotspot. Okay, so can you still see the screen?
Yes, sir.
Okay, great. Okay, thanks. Yeah, so it seems like the internet has gone here at my office. So, all right. Okay, so basically we can write any linear program in canonical form once we have a basis using this proposition, right? So it's a more direct way of figuring out how to do it. Of course, you can just do the row operations and try to figure it out that way. But this proposition can also be sometimes useful when you're doing some more theoretical stuff using the simplex method. Right? So you're proving something about the simplex method. This is often more useful. It's a direct way to get your canonical form or dictionary. Okay. Okay, so far so good. Of course, the big question is, how do we find a feasible basis? Right? Finding a basis is easy in some sense. If you don't care about how much time you take, you just need to find linearly independent columns, right? So you just need to find a basis, but it may not be feasible. So you may not have the property that the corresponding basic solution is non-negative. So how do we go about finding a feasible basis? Which is the same as asking, how do you figure out whether your linear program is feasible or not? Because until now, when we use the simplex method, we already had this canonical form or dictionary form, right? That already gave us a feasible basis. But what if we don't even have a feasible basis? So that's the next big question we want to answer. And as I said, this is the same as asking, how do we even find out whether a given LP is feasible? Okay. So we won't have time to go through the whole of this today. I actually would like to give it to you as a try it yourself problem along with some hints. Okay. So consider the following linear program. Maximize 2 minus 1, 2 x subject to -1 -2 1 1 -1 1. So let's say this is the LP given to you. Okay. It's not clear. I mean, you can try all possibilities, but it's not immediately clear how you can find a feasible basis here. So what we are going to do, there's a nice trick for resolving this issue. And that trick basically requires writing another LP and solving that LP to figure out whether this LP has a feasible solution or not, and also finding a feasible basis if there is one. So first of all, we can do one thing very simply. We can make sure that we don't have negative entries here, right? That's easy. We just multiply those constraints by -1. So let's do that one simple transformation to make things a bit easier. So I'm just going to multiply the top constraint by -1. Okay. So we can assume by doing this that the right hand side is negative. Right? So we may assume that B is non-negative. Okay, but even if the right hand side is non-negative, it doesn't mean that the LP is feasible. It could still be an infeasible LP. So let's call this as our given LP, with the right hand side being non-negative. And I want to give you as a try it yourself problem, and I'll give you some hints for it. What I want you to try is to write down another LP with certain properties, and solving that LP should give us information about the original LP that we are interested in, whether it is feasible or it is infeasible. And if it is feasible, we also want to get a feasible basis by solving the other LP. Okay, so write down another LP. We will call it auxiliary LP. Then let me just make it shorter so that I don't have to write this big word. With the following properties. All right, so the first property I want is I want the auxiliary LP to be feasible, right? Because if that is not feasible or we don't know, then we are again in the same problem. So we want to make sure that the auxiliary LP is always feasible. We also want to make sure that the auxiliary LP is not unbounded, which means that it must have an optimal solution. Right? Okay, so these two properties already mean that the auxiliary LP has an optimal solution. And finally, I want that the auxiliary LP will have optimal value 0 if and only if the original LP is feasible. The given LP is feasible. Okay, so I want you all to try this. You are given this LP. You need to come up with another LP with these properties. Okay, and just to give you a slight heads up, so this, what we are doing right now is called the two-phase simplex method. In the first phase, you figure out whether the given LP is feasible or not by doing this trick that we'll be discussing tomorrow with an example. And in the second phase, which only happens if the original LP is feasible, you solve the original LP and either get an optimal solution or you conclude that the original LP is unbounded. We will also discuss about when you can conclude it is unbounded, maybe tomorrow. Right? But we want to focus for now on the first phase. Right? So you're given an LP, you go through phase 1, in which you write down this auxiliary LP and you solve it. And if the auxiliary LP optimal value is 0, or let's say the optimal value is not 0, optimal value of auxiliary LP is not equal to 0, in this case, you conclude that the original linear program is infeasible. Otherwise, the optimal value is equal to 0 of the auxiliary LP. And in this case, we will be able to get a feasible basis of the original LP. Let's say the feasible basis is B. And we can also write a dictionary or canonical form, either using the proposition that we just proved or using some row operation tricks. Right? And write down a dictionary for this LP with respect to the feasible basis that we have found. And now you solve this LP because you have a dictionary, and you have two possibilities. Either you conclude that the LP is unbounded, which we still need to discuss by an example, or you find a dictionary with all the entries in the objective function being non-positive. So you know that the dictionary you have found is an optimal solution. It gives an optimal solution. Okay, so this is what is called the two-phase method, and tomorrow we will focus on phase one because phase two is something we have already discussed. Right, so this is called here. This is called phase two. Okay, but try this question, and we will discuss tomorrow with an example. All right. That's all for today. I'm here for another 10 minutes or so in case any questions or concerns.